I'm your host, the sometimes guilty but mostly innocent Jim Scott. I'd like to welcome you to the Grandmaster Series, where the challenges are focused on the data and the floor is lava! Wait, what? The floor is not lava? Well, I've set a pretty lofty expectation here, and I'm not sure I can back out of this. Okay, fine. So apparently, sorry to disappoint everybody, but on today's episode we'll be speaking with the world's leading experts in data science. We'll explore their approach and key learnings that have led to their amazing accomplishments and groundbreaking innovations in AI and data science. There are just a few things I'd like to point out before we get started. Anything discussed which is publicly available will be shared in the video summary below. If you have any questions during the video, you can submit them through chat, and we'll try to provide answers real time throughout and at the end of the episode. Also, please be sure to subscribe to our channel to be notified of upcoming videos in the Grandmaster Series. I would also like to point out that we have a phenomenal podcast series hosted by Paul Mahler. They're a lot of fun, and I encourage you to check them out and give them a listen. And then the final note that I'd like to share with everybody is soon we'll have our NVIDIA GTC conference coming up. It goes from April 12th to the 16th, 2021, and it's free for all to attend. During that conference, we'll have a Connect with the Experts with our Kaggle Grandmasters during that conference, and you'll be able to hear their experiences competing on Kaggle. We'll add links to all of this in the summary below. Now, I'd like to take the opportunity to introduce the team. First, we have Chris Deotte, Senior Data Scientist at NVIDIA. Chris has a Ph.D. in computational science and mathematics with a thesis on optimizing parallel processing. Chris is a 4x Kaggle Grandmaster. Next is Bo Liu. He holds a Ph.D. in applied math and statistics from Johns Hopkins University. Bo spent time working in fintech and has earned his Kaggle Grandmaster's title. Next is Dr. Christoph Henkel, a Ph.D. in mathematics with a focus on probability theory and stochastic processes, and is a senior deep learning scientist at NVIDIA. He's a 3x Kaggle Grandmaster. And last but not least, Jean-Francois Puget. He holds a Ph.D. in machine learning and has published over 70 scientific papers in peer-reviewed conferences and journals. He's a 2x Kaggle Grandmaster. Today, Chris will kick us off with a short history lesson in the current state of natural language processing. He'll also share best practices for using Hugging Face transformers. After that, the team will walk through 3 separate competitions where their best practices were applied in these competitions. Now that the stage is set, I'd like to hand it over to Chris. I'll be back at the end for some Q&A. Chris, it's all yours.
Thanks for the introduction, Jim. I think it's getting hot in my place here with this lava on the floor. I'm having a hard time. So we have a great show for everyone today. In today's show, we'll be reviewing all of Kaggle's NLP, Natural Language Processing, competitions of 2020. There were 4 competitions, and as you can see here, many Kaggle Grandmasters of NVIDIA, KGMON, participated and won top positions and won cash prizes. So the Grandmasters will be describing their specific solutions today. But before that, we're just going to discuss a general approach on how you can approach any NLP competition. So in the year 2020, it's very exciting for NLP. It's never been easier to build, train, and deploy an NLP model. If we jump down to the last bullet point here on the brief history, we see in 2019, Hugging Face provided a library and repository, which now all we need to do is just download a state-of-the-art pre-trained model. We can additionally train it a little more on our task, and we'll quickly have a state-of-the-art model. So how do we get to where we are today? Well, so some say that 2012 was the birth of the deep learning revolution because it was the first year that a neural network won the popular annual image classification competition, beating support vector machines. So shortly thereafter, we started applying neural networks to natural language processing. And in 2014 and 15, we saw recurrent neural networks, and they're pictured here in the top right. So in the picture, so when using an RNN, you don't actually use 4 of them. That's just for illustration purposes. There's actually only one RNN. And one of the disadvantages is if you're trying to input a sentence into an RNN, you have to input one word at a time and then wait for the result before inputting the second word. So if you want to input the sentence, the dog ran fast, you would input the word the and a state H0 into the RNN. Out comes the state vector H1. Then after that, you would input the second word dog and the state vector H1, and out would come a state vector H2, and so on. So you can see there's some disadvantages. So one is, you can't parallelize this. You can't train all the words at once. You got to wait for the result of each. So you can't use multiple GPUs. And also another limitation is the H vector is sort of storing the history, the memory, if you will, of the previous sentence. So as sentences get long, it has some difficulty remembering. So in 2015 and 16, that people started exploring attention. And then there was a famous paper in 2017 called Attention is All You Need, where a bunch of researchers at Google presented how to use attention for an encoder-decoder transformer. And this was great because now we were actually able to input the entire sentence all at once and have the entire thing happen at once. And this has many advantages. And then then this became popularized in 2018 when someone had pre-trained a model, basically pre-trained it on lots of text, and then they made the pre-trained model available as BERT. BERT only uses the encoder of the encoder-decoder transformer, and that was released in 2018. There's been a bunch of more models. So where we are today is we have all these models which are pre-trained with already a bunch of understanding, and they're just at our fingertips, and we can download and use them. So what is this thing called attention, which allowed us to come up with this transformer? So the transformer is shown in the dotted rectangle. And the advantage we had mentioned the transformer is basically the whole sentence goes in at once. So this is huge because it has an advantage over RNNs because since everything is occurring simultaneously, we can train now in parallel. We can break the network up into pieces and have different GPUs focus on a different piece. So this was a huge improvement. And the way attention works is this. If you were just to input a sentence into a fully connected neural network and everything is just connected to everything, there's too many parameters and the model will overfit quickly. So let me explain how attention works. So first, let's just get a basic understanding of the transformer. So an easy way to visualize a transformer is to imagine it as a bunch of vertical columns. So you have your sentence, and you first break your sentence into pieces, which are called tokens. Roughly speaking, you can imagine these tokens are words. And then you could visualize that each word sort of just goes from layer to layer straight through the transformer. So if you look at the word he right here, it goes in, and then each oval represents a numeric vector. So he goes in, becomes the green oval vector. Then in the second layer, it gets updated to the purple oval vector, and so on. And after the last layer, it's outputted as a vector of 768 numbers. So you can see that each word is sort of moving forward through the layers. So the invention of attention is how you create the new vector for a word. So using the formula in the top right, at each layer, we use self-attention to take the entire sentence and compare it with itself. And then we determine which words are related to which words. So if you look at the attention matrix in the bottom right, and you look at the row for he, the attention recognizes that the word he is related to the word dog. So now when you put in the original sentence, and let's only focus on the word he, when it becomes the green oval, it'll be modified from contributions mainly from the word dog. So that's how you form the green oval. And then in the second layer, you once again apply self-attention. And maybe this time the word he is related to the word hungry. So when you go from the green oval to the purple oval, you add contributions from the word hungry. And this moves along. And then finally, when you have the vector come out, the last thing, you now have a representation of the word he, which contains the full context of the entire sentence. So that's the basics of the words moving through the transformer using attention. Wow. So I need to take a breath. That was a lot to describe, but lucky for us, we don't have to worry about all those details because Hugging Face has made all of this available for us just to download. So as intricate as the last slide was, in only 3 lines of code, we can actually download a transformer and begin training it on our model. So that code is illustrated in this black dotted line. So if you wanted to use this repository, this library, you just pip install transformers, and then you just create a tokenizer and create a model. And then that's it. And then you basically would convert your data, your problem, and begin training your problem. So you can see with just a few lines of code, you can just download, the picture on the previous slide and begin training your model. So Hugging Face transformers have 2 huge advantages. So one is this easy to use API, a few lines of code lets you start training. And also their models are pre-trained. So this is actually maybe the most useful and impressive thing of what we have today is that these models have already, when we download them, they already come with a lot of learning. And you can see a list of some examples in this left column of some models. You'll recognize some of these names. In the media, you might have heard about GPT-3. We got some of its predecessors here. Those are autoregressive models. You've probably heard of BERT and Roberta. Those are some examples of encoding models, auto-encoded pre-trained models. And we got some sequence-to-sequence models. So what's so special about this pre-training? So here's the idea. Let's say your task is you have a couple thousand sentences, and you want to build a model which can classify those sentences and tell you if the sentence is positive emotion or negative emotion. So once again, you only have a few thousand. So if you only have a few thousand sentences, that's not enough data for your model to both learn the structure of language and to learn how the difference between positive and negative emotion. You just don't have enough data. So, but there's tons of sentences on the internet. We have Wikipedia, we've got public libraries of books. So it would be wonderful if somehow we can use that. However, we don't have labels, right? Nobody has actually read every line, every sentence in Wikipedia and said positive emotion, positive, negative. So we don't have labels on the internet, so we can't do supervised pre-training. But what we can do, and this is ingenious, somebody thought of doing unsupervised pre-training. So what they did is they took the transformer. Let's say we took a BERT, and we showed it everything, tons of stuff on the internet, billions and billions of articles on Wikipedia, billions of books, and you have it do this task. For each, you show it a sentence and you hide certain words, and then you try to make your transformer guess the missing words. So you just do this over and over and over, and obviously for your model to accomplish this task, it needs to start understanding the structure of language. So, and the example here on the left, you see the hammer blank the nail. So in auto-encoding pre-training, you allow your model to use all of the other words, and then using all the other words, it tries to guess the missing word. And in an auto-regressive pre-training, you give it the same sentence, the same missing word, but this time you only allow the attention to focus on the preceding words. So in this sentence, to guess the missing word, we can only focus on the hammer. So here's a table showing you some examples of transformers and what they were pre-trained on. So let's look at the column Roberta, and this will impress you. I know it impressed me the first time I saw it. So if you download the pre-trained Roberta from the Hugging Face repository, it has already read everything. So let's look in the row here showing data. It has already read every article on Wikipedia. It has already read 16 gigabytes of books from the corpus in English. It has already read 63 million articles from the Common Crawl news data set. It has already read 38 gigs of web text corpus. It has already read 31 gigabytes of Common Crawl. So do you know anybody has read this much stuff? No, but Roberta has read all of this. So Roberta has read all this stuff from the internet, and it has tried to fill in missing words. And then using that, it has already gained an understanding of language. And this was accomplished by using 1,024 NVIDIA V100 Tesla GPUs, and that was running for 24 hours straight. So that's how huge a task this was to pre-train these models. All of those articles, all of that computing power. But this is the amazing thing of Hugging Face. When you download a model, you immediately get all of that computing power, all of that pre-training, and then you begin training your model from there. So it's truly, truly amazing what we have today. We have access to all these models with all this pre-training already done. So we've already discussed a lot of exciting things on the current state of NLP. We discussed the Hugging Face library and repository, which allows us in a few lines of code to download a pre-trained model. And then we talked about training it on our own task. So the only thing we haven't discussed yet is specifically how would we use a transformer on a new task. So in the picture here, the transformer is in the green rectangle. So that's what you'll download from the Hugging Face repository. And then your job is to build the head, which is the purple rectangle. So let's take our original example of we have sentences and we want to classify them as positive emotion and negative emotion. And let's look at the picture on the right. So the sentence is, my lottery ticket won the jackpot. So is that positive emotion or negative emotion? So clearly that's positive emotion. Very easy for us. But this is how we would build a model. So our transformer, as we discussed, all the words go through all the layers, and out of the transformer, we have all these little numeric vectors, each one representing a word. We now build a classification head, which has a global average pooling layer, and then it has a single sigmoid unit, which now outputs a number between 0 and 1. And we'll train our model to output the number 1 whenever it sees positive emotion, and output the number of 0 whenever it sees negative emotion. And if it's unsure, it outputs some numbers in between. And let's look at a different example, the picture on the left. If we wanted to do question and answering, say you have a sentence and then you have a question and you want to find the single word in the sentence which is the answer to the question. Well, once again, you could put in the two sentences together with a separator through your transformer. Out comes vectors representing all the words. And you could put a dense layer and you could put a softmax layer, which will now output a whole bunch of zeros, and it'll put a 1 exactly wherever the answer is. And in this case, you could say it put a 1 right where the word dog is. So the question was, the dog jumped the fence was the statement. And the question was, who jumped the fence? And you can see the model, it put a 1 on the word dog. So it correctly answered the question. Cool. So you guys now know all of the basics on how to build an NLP model. We now want to look specifically at the image competitions, the Kaggle image competitions, and we're going to discuss how these ideas were used and improved upon. So these are the competitions we'll be discussing, and we will first discuss the bottom left, the TensorFlow 2.0 question and answering competition. And we have Bo with us today, who will describe his solution and other solutions in that competition.
Okay. Thank you, Chris. The next slide, please. Okay. So I'm going to talk about this competition. But before we dive into the competition itself, I want to briefly talk about the question answering task in NLP. So QA task is one of the core NLP tasks. And the most common format of question answering is the so-called extractive question answering, which means that the answer is a subset of the given paragraph. So this way is easy for the model to generate the answer, and also it's easy for the system to evaluate the generated answer. So in the QA space, the most popular data set is called a SQUAD dataset. It's created by researchers in Stanford. It stands for Stanford Question Answering data set, SQuAD. So it's very popular. It's basically the ImageNet in the question answering domain. And the format is that for each data set, there's the triplet of paragraph, question, and answer. So all the paragraphs are from Wikipedia articles. So for example, on the top right is one of the example. It's a paragraph about Harvard Business School, and on the bottom right, there are 2 questions and their answers. So you'll notice that for each question there are not 1 but 3 ground truth answers. That's because for some of the questions, it's even for like two different human beings, they don't give exactly the same answer. For example, if the answer is somebody's name, then the answer can be the whole name, or can be the first name, can be the last name. So by asking the annotators to give 3 different ground truths, it gives the model some leeway in terms of the flexibility of the answer. And so when the SQuAD dataset was first introduced, it's called version 1.1. In version 1.1, all the questions have answers. So which obviously is not the case in real life. In real life, a lot of the questions, they don't have answers. They are unanswerable from the given paragraph. That's why in the later version 2.0, they introduced some of the so-called unanswerable questions, which make the dataset somewhat more realistic, and at the same time make it a little bit harder. So when they created the dataset, the creators asked the human to answer the questions. So they have a human performance baseline. So if you look at the bottom left, this is the leaderboard of SQuAD 2.0 as of today. And on the very top, you see the human performance is about 89 F1. And what is interesting is that the top of the leaderboard, the top 1 and 2 entries, they already surpassed the human performance by a few percentage points, which means that this SQuAD dataset is kind of solved. And SQuAD 1.1 was solved like a long time ago, but SQuAD 2.0 was solved after the invention of the BERT and the other transformer models, which means that we need it's time for a new and harder data set. So which leads us to the next slide. So this new data set is called natural question data set. They are created by researchers at Google. So the fundamental difference between SQuAD and this data set is the way that they are created. So for SQuAD, the annotators were given the Wikipedia paragraph, and they were asked to read the paragraph and come up with questions and answers. So in a way, the questions are like man-made. So it's like when we were in middle school and high school, we were doing the reading comprehension question, right? We read the paragraph. There are a couple of questions that are like specifically designed for that paragraph. So the wording and the logic of the question like may be like very similar in the original paragraph, which make it easy. So a model may not understand the meaning of the sentences. They may just do some simple pattern matching and can still get the questions correct. But in this Google's natural language dataset, they are created totally differently. So they use the real questions typed by real users into the Google search and get a bunch of those questions and filter out unanswerable questions and filter out a lot of like subjective questions. Like if you ask who's the best Kaggler of all time, there's no objective answer. Or if you ask why am I not smart enough, there's no object. So they only keep the knowledge-based answer, which can be associated to a Wikipedia page, and they give the question and the whole Wikipedia page to the annotators, and ask the annotator to give both a long answer and a short answer. So the long answer is a paragraph containing the answer, and the short answer can be a span, like in SQuAD, or for a yes/no question, the answer can be yes or no. And some of questions, they are not even answerable from the Wikipedia page, so it can be also no answer. So the type of the answers is also more complicated than in SQuAD. And since they are Google, they have a lot of data. So the data set is naturally larger than Squat. And as I mentioned, since it's a real question, it's harder because when the user type a question, when you type a question like in Google search, you don't know which Wikipedia page is associated. So you don't know, even look at the from the user perspective, they don't read the Wikipedia page in advance. So the wording and the way of thinking can be totally different, which make it much harder. Next slide, please. So this computation is just based on this natural question data set. So the data set is this data set, and the metric is also the F1, which is the official metric for this data set. And luckily for us Kagglers, the author of the natural questions data set, they also built a BERT-based baseline called BERT joint, because the natural question data set was created after the invention of BERT. So they were able to build a BERT-based baseline. So here are the idea of the model. First, they jointly predict both the long answer and short answer, hence the name BERT joint, sometimes called joint BERT. Jointly means that one model predicts both answers. They don't do like pipeline approach. They don't do separate stages. And for the output, similar to Squat, you want to output the span of the answer, which means the location of the start of the answer and the location of the end of the answer. So if there is a short answer existing, the location of the span is the short answer. If there is no short answer available, then the span will be the long answer, which is the paragraph. And there's the additional output, which is type. Type meaning that whether it's yes, no answer, or whether it's a short answer, whether it's long answer or no answer. And since Wikipedia page can be very long, right, can be like dozens of paragraphs, so they cannot fit all the whole page into one training sample. So in Squat, the paragraphs are shorter. So in most cases, the whole each data set can be fit into BERT with no problem, because the default BERT has 512 tokens. So for this question, for this problem, they need to like split the whole Wikipedia page into different chunks, then fit into the model. And since Wikipedia page can be very long, and the answer is usually appear in one place, so that means that if you split into like 100 pieces, maybe only one piece have the answer, then there are 99 pieces without the answer. So the ratio of the null segment is very large by default. So what they do when training the model is to downsample the percentage of the null segments. And finally, in Wikipedia page, usually the answer that appear in Wikipedia page usually appear in the very beginning, usually the first paragraph or the first 3 paragraphs of the page. So it's kind of important to indicate to the model which paragraph it is of each sentence. So they also introduce some special token to mark the position of each paragraph, like paragraph 1, paragraph 2, paragraph 3. They introduce some special tokens and add it to the model. So the one of the author of the BERT joint, which is also author of the BERT. So I think they tuned this model, they tuned this baseline very well. So it turned out that it's kind of very hard for us Kagglers to try to beat this baseline using only BERT. So next slide, please. Oh, here is the illustration of this BERT joint BERT baseline. So on the left is a paragraph. It's a figure I took from the original BERT paper. So it's illustrated what Chris already did. So basically, is that you fit the question and the paragraph separated. You concatenate them together and fit into the BERT. For this case, question usually is short. Question usually like 10 to 20 tokens, and the rest of the space like 490 something tokens. They are left for the paragraph. So, but the Wikipedia page, as I mentioned, can be very long. You need to be like split into multiple segments, as illustrated on the right. But they are not just directly split. They have to have some overlap, as you see on the picture. This is because for the special case that if a short answer or a long answer happen to be like in between, or how do I say it? If the short answer is into to prevent the situation that the answer is cut into half, so they need to have some overlap to prevent that situation. And next, please. Okay, so our team, I teamed up with another KGMON, Jiwei Liu, and we got into 7th place. Here, oh, by the way, this competition has another twist. So the name is called TensorFlow 2.0 question answering, but they don't they want to promote TensorFlow 2.0, but they don't strictly enforce the use of TensorFlow. So, and in fact, the winning team, Guanshuo, both the winning team, Guanshuo, and the 3rd place team, the KGMON, Christophe, and Jean-Francois, they used PyTorch and with Hugging Face. And not only that, the 3rd place team, they put the team name as in PyTorch we trust, which I found it very amusing. But I did the competition before I joined NVIDIA, so I didn't have a lot of GPU resource, and I wasn't using a Hugging Face transformer library at the time. So our solution was based on the baseline, which is in TensorFlow 1. So we made some improvements based on the baseline, as most team did. But since we didn't use the transformer, we only stick to BERT. So here are some of the improvements that we did. First, in the baseline, they used the original BERT weights, and we used a better pre-trained weights called the whole word masking weights. And we further fine-tuned the model on Spark 2.0. So the model see more data because after the pre-trained BERT, we further fine-tune on the Spark data. So the model sees not only natural question training data, but also the Spark 2.0 training data. Since we are not using Hugging Face, we did the fine-tuning ourselves. But if you were using the transformer Hugging Face library, I think they already have the weights pre-tuned on Spot. And next is that, as I mentioned, the baseline, they use downsample. They downsample the null weights or the negative sampling, but we noticed that the model have different performance for the answerable and unanswerable samples. So we use a different sampling rates for negative samples. So we use a bigger negative sampling rates for the unanswerable because we found the model is weaker to predict the unanswerable samples. And there are some other parameters that we tuned in the model, like the stride, like how overlap they are for each segment. And max context meaning that some of the Wikipedia can be like very, very long. So you need to have a cutoff. So the default is 48. So only use the first 48 paragraphs if there are more than 48. So that's another parameter you can tune. Because in some extreme cases, the answer can appear after the first 48 paragraphs. But the trade-off is that if you include more paragraphs, the percentage of the null sample will be even larger. And also we trained both the cased and uncased version of the BERT just for the diversity purpose for the ensemble. And we also use a augmentation approach called sentence order shuffling. The idea is that for the paragraph containing the ground truth short answer, you can actually shuffle the order of the sentence randomly because the order doesn't really matter that much. So by shuffling, it's like give the model more diversity. Lastly, we did some yes and no post processing, meaning that for if the model predicted the probability of the short span is lower than a certain threshold, then meaning that it's yes or no answer. We just took the yes and no. So that's the gist of our solution. Next, please. But how did some other teams beat us? Here are some of the smart ideas of other top solution ideas. So first, as I mentioned, people use Hugging Face and PyTorch. I mentioned the first and third place. Actually, the second place, which used the TensorFlow 2.0, he also used the Hugging Face. So Hugging Face supported both TensorFlow and PyTorch. And because some of them use the Hugging Face library, it's easier to incorporate into new models, newer, better models than BERT. So for example, Roberta and Albert were used by the top teams. We will actually also use Albert, but as I said, we didn't use transformer library, so we had to like read the Albert's original repo, which in TensorFlow, and convert it into the format of this computation, which took a lot of time and effort. Especially the tokenization is hard to convert. And Roberta we didn't use because it was Facebook's model, so it's was not in TensorFlow. And another smart idea is that in NLP models like BERT and Albert, they can be very large. So during the 9-hour inference period, it's hard to fit a lot of models. So the winning team, he has a very smart idea, is that use a smaller model to predict the candidate, then use the larger model to do the final prediction, which dramatically reduce the total inference time. Another smart idea is that you can actually modify the model head, model output. So instead of predicting all the different type of answers, you can make the model only predict, for example, the short answer, because the long answer is always the paragraph containing the short answer. Or you can make the model to only predict short and long answer, not the yes and no answer, and do some ensemble and post processing on top of that. And the next is that in addition to the special token in the baseline, some teams they have special token for other HTML tags, because in the Wikipedia page is a web page, right? They have different kind of HTML tags. Some of them can give the model useful information. And finally, the winning team used hard negative sampling, because in the original data, a lot of the null samples are very easy for the model. So by using hard negative sampling, you have the model converge better. So that was the TensorFlow 2.0 question answering competition. Next, Christoph will present the Twitter. Christoph was in the top 4 in all the 4 NLP competitions last year. So he's an NLP superstar on our team. Go ahead.
Yeah, so thank you both for introducing. I'm very glad to talk about the tweet sentiment competition. That was one of my favorite ones, which is from the task very close to the TensorFlow 2.0 questioning. In this competition, I teamed with a young data scientist from Vietnam, and we finished on 3rd place out of over 2,000 teams. So the task here was that given a specific tweet and a sentiment for that tweet, so being positive, negative, or neutral, you need to figure out what phrase supports the sentiment. So take, for example, the tweet, "My ridiculous dog is amazing." And you need to figure out what phrase would support the sentiment positive. Then the answer might be "is amazing" or "just amazing." So it's a total level span prediction or question answering. That's the same word. The competition data was quite small, so we only had 28,000 tweets for training and was evaluated on only 4,000 tweets. We had 3 sentiments: positive, negative, and neutral. And the public-private leaderboard split was 30 and 70. They had an interesting metric for this competition. So they used Jacquard on word sets, which is like intersection over union over specific word sets. Next slide, please. So our solution, surprise, surprise, is an ensemble of transformers. We used 3 different transformers, namely Roberta Base, Roberta Large, and BART. Large was quite new at that time and was also from Facebook. From a software hardware perspective, we used Hugging Face and PyTorch, like I used in all of the 4 NLP competition last year, and I trained on an NVIDIA DGX station. In our ensemble, we used 2 different modeling approaches, which ensembled quite well. One was question answering on word level using a so-called beam search edition. And one was a quite new, innovative character level span prediction, which, although it's on character level, still uses the transformer which were pre-trained on word level. And I will talk about that a little bit later. Next slide, please. So what was the main challenge in this competition? So question answering, so the tweet sentiment extraction was very close time-wise after the TensorFlow Q&A. So all the Kaggle competitors could already read what others has done in the previous competition, and the baselines were quite high already, and you need to address specific challenges in this competition, which were mostly related to very noisy annotations. And those noisy annotations were of 2 types. The first type I illustrated in the first 3 examples. So given the same tweet, the human annotators can annotate very differently. So given this tweet, they can annotate and the sentiment positive. They can annotate just like, or I like it, or the whole tweet without the exclamation marks. So it's a little bit very noisy, a little bit random how the human annotators annotate this. And then the second, also very crucial noisy part, that in this tweet here, you guys didn't say hi or answer my question, but nice songs. You can see that the annotators actually annotated in the middle of the word. So they not annotated the word nice, which led to the positive sentiment, but also half of the word but, which is a little bit strange. And it's like the core question of this competition, why this is happening and how you can address this issue. So additionally to the noisy annotations, the test set was also very small, and you could not really rely on the public leaderboard for any feedback. Next slide, please. So since you cannot rely on the public leaderboard, a key point to performing well in this competition was a very robust cross-validation setup. So we only relied on our local validation, but also that was quite hard and noisy because also the training set was very small. So what we did there to increase the robustness was that we not only trained with a k-fold, so a 5-fold to be a specific validation scheme, but we also trained each model on 3 different Zs for stability. So for each fold, we basically trained the model 3 times and then averaged our results. And additionally, we tried not to use any, although it might be seen as minor, peeking into the validation data. So no early stopping, no checkpointing of best validation scores, to also avoid overfitting to the validation set, because the validation set is the only thing we had basically to tune our model, since the leaderboard data was very small. Next slide, please. So when it comes to transformers, the tokenization is very important. And in this specific competition, it turned out that this wrong annotation of half words was related to spaces introduced by cleaning up the data before it went to the annotators. So since it was like tweets, and tweets can have like huge noise in them and huge like other artifacts and text, like hashtags, user tags, emojis, And all these things were cleaned before it was annotated and left consecutive spaces, and those spaces introduced the noise. And it was very, very important to handle these spaces and to catch the signal that comes from those spaces in the tweets. And for us, the Roberta tokenizer was the best for this case, because the Roberta tokenizer catches each space for the model. So a space is even a space is a token for the model, so to say, which is quite the opposite for BERT. BERT just like gets rid of all the spaces, and you cannot conclude anything from the space signals at all for this competition. One disadvantage of Roberta tokenizer, though, is that it will, for punctuations, it will keep punctuations together. Like in the example here, I like it. The three, you can see on the right, the tokenization then, where this G with a dot is like the way how they encode spaces. But the important thing is that at the very end, the 3 exclamation mark, they are seen as one token, which is also not optimal for the model, because then the model cannot predict a single exclamation mark as part of your answer span. So to fix it, we basically edited or manipulated the Roberta tokenizer to split up this consecutive exclamation marks, for example. And for the character model, which I also will explain, we didn't use any pre-processing at all, because that will work at the end of the day on a character level, and you don't need any pre-processing. Next slide, please. So that's the architecture of our word-based or token-based span prediction model. So it's very, very similar to the question answering model, which Chris presented, or the TensorFlow 2.0 question answering model, which Bo presented, but it has an additional twist. So taking this example sentence below, you put it through the pre-trained transformer, which is standard, but then for the custom head, you do something special. So instead of predicting the start of the span and the end of the span at the same time, you first predict the start of the span, and then conditionally on that, you predict the end of the answer. And how you do that technically, you predict the start of the span normally, and then you know basically which token is the start, and you can see here by this red node, you get the hidden representation of the start. You concatenate it to every token you have in your sentence. So you have the twice number of features for each token, which becomes from 768 to 1532. And then use that hidden representation, which is basically the original representation plus the representation of the start, and use that with a softmax for predicting the end of the span. And that works a little bit better than the standard procedure for question answering, and was the core of our word-based model. And this type of head, it's called a beam search head. Okay, next slide, please. Now I want to explain the character-wise span prediction, which I'm very proud of, because as far as I know, nobody has done this ever before. Anyway, and it's quite an innovative approach, because I thought a long time, how can you predict parts of the words which are on character level, but still use the knowledge which is contained in the pre-trained transformer? So as Chris explained, the pre-trained transformers, they contain billions and billions of web pages, books, Wikipedia articles, and so on and so forth. And in order to do well in any natural language tasks, you need to use that knowledge. But that knowledge was trained on word level. So how can you use that knowledge but predict something on character level? So here, what I come up with. So you put the tokens on word level through the pre-trained transformers, which give you the hidden representation on a token level. And then, that's the clue, you replicate each hidden representation for each token as often as the token has characters. So as you can see on the right, the word songs, which has 5 characters, the hidden representation is replicated 5 times, and it becomes 5 times the same node representing a hidden representation of each character, which per se will have exactly the same numbers. So at some point now you need to learn interaction between the single characters. And for that, I tried a lot of different model architectures, so CNN, RNN, also transformer. But it turned out that on top, the RNN worked best to learn this additional character interaction. So I stacked 4 layers of this bidirectional RNN to learn additional character interaction, and added the span prediction head on top, and that enabled me to do a character-wise span prediction which utilizes spaces. And with that, we had a very innovative additional model for our ensemble, and that secured us this top position. So I guess that's from my side. And I give over to Jean-François.
Thank you. All right, so I teamed with Christophe and Ahmed, who's not on the call, but also from NVIDIA for this competition. I teamed with Christophe in 3 of the 4 competitions here. I recommend teaming with Christophe on NLP. And this one was ending like 1 week after one of the other competition we discussed. And with Christophe, we said, oh, maybe we can run, now that we are on NLP Lava, we can keep the momentum. And Ahmed has had started before, so we teamed, and we had 4 days. And incredibly, we finished at a very high rank in only 4 days of work, which proved the point we're making, that using Hugging Faces, you basically only need to create, or not, just use a given head on pre-trained transformer model and just fine-tune a bit. That's what we did here. And I'm not even sure we use custom head, because the problem was just a binary classification. So the problem was we were given tweets. Was it tweets? No. We were given comments in English, and some were labeled as toxic and some were not. Then we had validation data in 3 languages, not English, but Spanish, Italian, and Turkish. So we had the host were hoping that we would train a model in English that would generalize well to new languages. And to make sure in the test data, they added even more languages, Russian, Portuguese, and French. So having on the team a Turkish, Ahmet, and me as a French was good to validate some prediction in some case. But what we did, fortunately, some people shared translation of the training data, because in a previous competition, it was shown that translating back and forth between English and other languages was a good way to augment data. So here, people translated using Google Translate API the training data in the 7 languages. So we could train a model in 7 languages upfront, which was good and bad, because if we train the model on all the training data in 7 languages, it overfits. So we decided to split in 7 pieces, making sure that a given command translation is only in one of the split, in one of the folds, so that the model only sees a comment or its translation only once per epoch. The other tricky part in this competition is the metric, which is ROC AUC, so area under the ROC curve. Because this metric looks at the order in which you predict, the order in your prediction values. So it's not, your model is not supposed to output a 0 or a 1, but it will output a probability that a given comment is toxic. And the relative value of the prediction matters. And the issue is if we have 7 different languages, and we must make sure that the calibration of probabilities per language are consistent across the languages. So I'll come back to this. Fortunately for us and for NLP in general, Hugging Faces did a good work. And at the time, they had a package, a pre-trained XLM, so cross-language model based on Roberta. And you see a common point, Roberta is often the best, or one of the best model in at the time in these NLP competitions. So most of the top teams used XLM, the same pre-trained model. And the difference is how we fine-tune. We spent time, because training time was quite long, and the comments are coming in very different sizes. So if you just randomly sample the comments and construct batches like this, you basically need to pad every comment to the longest in the batch, and you end up with long comments with a lot of padding. So instead, we just sorted the comments by their lengths and take as batch consecutive comments, which minimizes the amount of padding. And of course, we randomly choose the batches themselves. So we implemented the custom data loader in PyTorch. And we got, I think it was more than 2x speed up actually. Next, please. Then the strategy is quite simple. So we start from the 7 copies of the training data in each language plus the original one. We shuffle it so that and split in 7 parts so that each part contains one variant of the comment, either the original one or one translation. And so the 7 variants of each comment are in 7 different splits or folds. Then we train a model per fold, XLM, a Roberta large, and use that, the average of the model prediction to predict Russian. Then we were given, remember, the validation data directly in Turkish, Italian, and Spanish. And augmenting training data with translation is fine, but the translation adds some noise. It's not perfect. So we fine-tune on perfect ground truth using valid CSV. And then we predict Portuguese and French because they are Roman languages similar to Italian and Spanish in a way. And then we fine-tune further on each Turkish, Italian, and Spanish because we have a perfect ground truth for these. You see, fine-tuning is only 1 or 2 epoch. That's really the beauty of, if you have enough data, of this pre-trained NLP model. They need a small amount of data to fine-tune, actually. But as you see, the predictions are coming from different models. And there is no reason why the probabilities are calibrated the same way between the Russian coming directly out of training, fine-tuning, and say Spanish that went through 2 more epochs. So as the last step, next slide, please. We scaled the logit by a factor, and the factor was found by looking at the average prediction, so average probability in the public test data. And for this, we probed, so used some submission to find the average probability of a command to be toxic in the public test data. And you see how you set one language to be all toxic and the rest to 0. And from that, you can find these probabilities and then the logit mean, and then you can adjust so that all the logit means are the same across languages. And this bought us 10 ranks. So if you want to fare well on Kaggle, you don't need to worry about this. If you want to reach the top, you need to worry about this. It makes a difference between 14 and 4th. And not just in that competition. It happens, say, in one competition out of 3, that post-processing makes a big difference. With this, I will stop. The top teams did something similar, except they blended more models or used stacking. But we all use XLM Roberta large, as far as I remember. And with this, I will give it back to the host, probably.
Fantastic. That was really great. Somebody's audio is feeding. There we go. Hey, thank you all for sharing those details on these competitions and how you ended up with the best of breed solutions. I'm going to preface all my Q&A with NLP is not my area of expertise. But with that being said, you mentioned some models like Distilabert, and I'm really curious, are there benefits to using models with less parameters?
Yeah, so I'm a very great fan of Distilabert because it enables you to iterate way faster. So when I start on an NLP competition, I start with Distilabert and I keep going with that as long as possible, just because it trains 5x faster than other models. So you can set up your pipeline with this. You can evaluate general ideas, and you are like way ahead of other competitors who use stronger models, but slower models also.
So before I joining NVIDIA, in my previous company, I actually used Distilabert a lot because there I didn't have a lot of GPUs, and we actually used the free Google Colab for a lot of model training. And Distilabert is like perfect. The model is smaller, and performance, like in day-to-day data science, you don't really care about like 1% like difference in performance. In Kaggle, we obviously want to use the best model. But like for regular data science, a lot of time Distilabert can achieve like most what they want.
Yeah, I think that's really helpful consideration for the data scientists out there. The next question that I've got is, recently NVIDIA announced the release of the A100 with 80 gigs of memory. Would this be a factor in producing better results? Perhaps help with improving batching?
Yeah, definitely. So batching is one thing that you can basically make twice the batch size, which is quite important for these huge models. So if you take like one of the largest models, the batch size is quite small in training. And small batch sizes has a lot of disadvantages. And if you can double the batch size, that has a huge impact on performance. And additionally, this with a lot of memory, you can also feed way longer sentences to the model. So if you have double the memory, you can basically at same batch size feed double the length of sentences, which is also quite important for complex tasks where you analyze complete Wikipedia articles, for example. So for me, it's a game changer to have that much of GPU memory.
That's great. And the last question that I've got is, so I've been fortunate enough to learn a lot about speaking and engaging communities with language barriers. I've spoken publicly in countries like South Korea and in Japan. And one of the things I learned very early on was not to use things like idioms or generally sarcasm. We've become really quite accustomed to using very localized phrases, and I'm curious how things like sarcasm or even idioms come into play within the realm of NLP.
So in deep learning era, like this kind of problem can can be more easily handled, because as Chris mentioned, all the models, they pre-trained on like tens of millions of data, right? In this data, I assume like sarcasm and idiom, like they appear. So the model can over time learn all those behavior. Like before deep learning, like when people use things like TF, IDF to do NLP, like it's harder, because like for like double negative, like it's harder if your the TF IDF like length is not enough, like it's harder to catch off things like that.
Great. All right. Well, Chris, Bo, Christophe, Jean-Francois, I'd like to thank you very much for spending your time speaking with myself and all the viewers. I think not only have I found this conversation very enlightening and educational, but I think all of our viewers will have a lot to take away from it as well. To all the viewers, thank you so much for spending part of your day with us and taking the time out of your otherwise busy schedule to enjoy this episode in the Grandmaster Series. I'm Jim Scott, the one whose mother said he has the perfect face for podcasting. Have a great day, and may all your data science be accelerated.